Hello there, Mr. Sutton here, bringing you the BC Calculus Chapter 3 Quiz Review Number 1 solutions on power rule, differentiability, and graphs of derivatives.
So on this problem, we're just trying to find the derivative of this function. Since these are all power functions, all power terms here, we can just use our power rule. To use that, we multiply the exponent by the coefficient. So 3 times negative 4 is negative 12. And then decrease the exponent by 1. So this would be negative 12x squared. And remember, you can only do this when you have a constant exponent. So this next one then, that would be 18x, followed by, this is the line rule here, this is just a line with a slope of negative 1. So this would be negative 1, because that's what the derivative slope is, or the derivative is the slope. And then slope of 7, well 7 is just a constant function, so its derivative is 0, which we don't bother writing. To find f prime of 2 on this function, we first need to take the derivative and then plug 2 into it. So using my power rule for the derivative, 14 gets zeroed out. Derivative of negative 6x is just negative 6. And then derivative of 20x cubed, 3 times 20 gives us 60, and then we'll have x to the 3 minus 1, so that'll be x squared. And now I have to plug 2 into this. F prime of 2 is just going to be negative 6 plus 60 times 2 squared. 60 times 2 squared is 240. Minus 6 gives us 234. To take the derivative of rational functions like this, we first try converting it into just exponential functions. So I'll rewrite this as 5x to the negative third. And then this one I'll have as negative x to the negative 2. And this one I can actually reduce a little bit. Just subtracting the exponents, we have 1 minus 2, so that's 18 to the x, or 18 times x to the negative 1. Now we go through and just use our power rule. So I have negative 15, and then I'm going to have x to the negative 3 minus 1, so be careful there. That's going to be negative 4. Next we'll have, this will be positive 2 times x to the negative 3. Finally, negative 18, x to the negative 2. To take the derivative of radical functions, we rewrite it with a fractional exponent. So I'm going to rewrite this first one as x to the 3 over 6. It's always going to be the power over the root in that fraction. And then for this next one, we'll have 3x to the, now this is in the denominator, so I'm going to have a negative exponent, negative 1 over 3. And let me rewrite this first one as just 1/2, so it's a little easier to take the derivative of it. Okay, taking the derivative now, just using the power rule here. This first one I've got 1/2 times 1, so that's just 1/2 out in front. X to the whatever 1/2 minus 1 is, so that's negative 1/2. For this next one, we've got negative whatever 3 times 1/3 is, so that's actually negative 1. And then this will be x to the negative 1/3 minus 3/3. So that'll be negative 4/3. Okay, let me go ahead now, and this one they actually wanted f prime of 64, so we have to plug 64 into all of this. And to do that, I think it's easier if you convert it back into radical form. So this first one I can rewrite as 1 over 2 times the square root of 64. And then for this last one here, this is going to be minus, and we'll have 1 over, this is going to be the cube root of 64, and that's being raised to the 4th power. Okay, so for this first term, now you have all constants, so if it is a free response, you could leave it like this. But if it's multiple choice, you'll need to simplify. So just to get a little practice with that, this first one, we've got square root of 64, which is 8. 2 times that is 16, so 1 over 16. For this next one, cube root of 64 is going to be 4. Raising that to the 4th, we get 256. So this is 1 over 256 that we're subtracting. Common denominator would be 256. 1 over 16 is 16 256. So subtracting 1 from that, we get 15 over 256. On this problem, they're asking what is the limit as h approaches 0 of all this stuff. So this is actually the limit form of the derivative. We can recognize this because we have something with h minus something that doesn't have h all over h. As h approaches 0, you're basically taking an average rate of change and turning it into an instantaneous rate of change. So this is just the derivative of some function. All right, well, let me identify the original function here. You just have to look at the x plus h term and see what's happening to that to see what the original function is. So we really have 2 over the 5th root of x as the original function. To take the derivative of this, let's first rewrite it with a fractional exponent, and it'll be negative 2 because this x is in the denominator. So this is going to be 2x to the negative 1/5. Using the power rule on this, I'm going to have negative 2/5 out in front, and then this will be x to the negative 1/5 minus 1, so we're subtracting 5/5 to get negative 6/5. For this problem, we're being asked about the limit as h approaches 0 of this craziness. Now this is actually the limit form of a derivative, and we actually have a number that we're plugging into the derivative. This 2 plus h in here tells me that I'm plugging 2 into f prime for whatever this function is. Let me start by writing the original function. So whatever's happening to this 2 plus h, that is the original function, at least in this first term here. This minus 40 is actually 5 times 2 to the third, but it's kind of hard to see that. So this is really the function 5x to the third. Now the derivative of that, f prime, that's going to be 15x squared. But we actually want to figure out f prime of 2. So that's going to be 15 times 2 squared, 15 times 4, giving us 60. For this problem, we want to identify the x values at which this function is not differentiable, and then write the intervals of differentiability using this. So going from left to right, we see our first non-differentiable spot at negative 11. This is actually the hardest one to spot, but this is a vertical tangent, a slope of exactly infinity at exactly one spot. It's a perfectly vertical tangent line. So we have a vertical tangent at x equals negative 11, and then as we move to the right here, we see this pointy spot. This is either a corner or a cusp, depending on whether you think this is kind of an infinite slope right here. Either way, we can call it a cusp. So this is a cusp at negative 8 for the x value there. And that's not differentiable because you either have an infinite slope if it's a cusp, or if it's a corner, you have an abrupt change in slope that does not go through 0. All right, let's keep on moving now. Over here we have a discontinuity at x equals negative 4. If a function is not continuous at an x value, it's not differentiable. And at long last, we have another cusp at x equals 1. So to write the intervals of differentiability, we just write the intervals around these non-differentiable spots. So going from left to right, we have negative infinity to negative 11, followed by negative 11 to negative 8, union negative 8 to negative 4, union negative 4 to 1, union 1 to positive infinity. To figure out if a function, a piecewise function specifically, is differentiable at an x value, the border value here, we have to first test it for continuity. Once we've done that, we can check out the limits of its slopes to see if those match up. So checking continuity first, we have to take the left and right side limits and also the function value at x equals 3. So left side limit at 3, that's going to just be plugging 3 into this x less than 3 function right here. So 3 squared gives us 9 for that. Next, right side limit at 3. Now we're plugging 3 into this bottom rule. 7 times 3 is 21, minus 12 is going to be 9. So the limits match up. Let's check out the function value. Function value happens to have the same value as the right side limit because the equals is in the second rule here. So f of 3 is also going to be 9. Now we have to show f of 3, even though it happens to match up with one of these limits, because on the very next step, we're trying to show this thing is continuous. And to do that, we have to show that the value of the limit matches the value of the function. And if we show that, then we implicitly show that they both exist, which is the other two conditions. So we can say here, limit as x approaches 3, the two-sided limit, equals f of 3. Therefore, we are continuous at x equals 3. Well, this is not enough to show differentiability, but it's a good start. Next, we have to find the left and right side limit of f prime for this function. So left side limit of f prime, we're basically taking the derivative of this first rule and plugging 3 into it. That's the limit as x approaches 3 of 2x. and that's just going to be 2 times 3, which is 6. Next, we need the right side limit at x equals 3. Now we're taking the derivative of the second rule, which is just 7 no matter what you plug into it. Well, 6 and 7 are not the same. Since the left and right side limits of f prime do not match up, we can conclude that our function is not differentiable at x equals 3. Now, a few other ways this could have gone. If we had found the function was not continuous at x equals 3, we would have then concluded it was not differentiable right away. If we had found that the function's f prime limits did match up, that would have been enough to say, okay, this function is differentiable at 3. To figure out values of a and b for which this function is differentiable, we need to basically show that the function is continuous and differentiable, or at least go through the steps of that proof that we did on that last problem. And in doing so, we'll get some equations that we can use to solve for a and b. So let's start with continuity. So I need the left and the right side limits in the function value at x equals 1. Left side limit at 1. We're plugging 1 into this first function here. So 3 times 1 squared is just 3. Right side limit at 1. Now we're plugging 1 into the second rule, the x greater than 1 rule. So a times 1 minus b is just a minus b. And since we're trying to show the function's differentiable, we need to prove it's continuous. So we need to at least note what f of 1 is going to be on this. F of 1 is just going to be the same as our left side limit because the equals 1 is part of that first rule. So that's 3. All right. Well, if this function is continuous, that means these three things have to equal each other. The limit and the function value have to match up. And for the limit to even exist, the left and the right side limits have to match. So basically 3 has to equal a minus b. Not enough to solve for a or b, but let's keep going, because now we're going to do the left and right side limits of f prime, and hopefully that'll give us another equation that we can use to get to the bottom of this first one. So left side limit of f prime as x approaches 1 from the left. We've got basically the derivative of this first rule, which is going to be 6x, and we're taking 1 and plugging it into that. So that gives us a value of 6. Okay, let's take the right side limit now as x approaches 1 from the right of f prime. So for that one, we're just taking the derivative of this second rule. So going from left to right, derivative of ax is just a, because a is a constant. Derivative of minus b, well, b is also a constant, so it gets zeroed out. So this is actually just a when all is said and done. Now we know that the left and the right side limits have to match up for f prime if the function is to be differentiable. So that means that 6 and a must be the same thing. Well, if a equals 6, we actually have enough to go back and solve for b in this original equation here. So let me plug 6 in for a in this equation, so I can write 3 equals 6 minus b. And then solving for b, I can add b over here and subtract 3 to get b equals 3.
Let's see what we got for our critical values. For non-differentiable spots, we have this asymptote right here. So that's going to give us an asymptote on the derivative as well. Here's a cusp on the original. That's an asymptote on the derivative. We've got infinite slopes. You might have noticed that we have a vertical tangent right here. So that's another asymptote for the derivative. And we have a few constant sort of non-differentiable places. So right here, for example, this jump, this is an almost zero slope, but we're switching immediately to a slope that's fairly negative. So I'm going to put another open dot down below here where we're going to start another branch. And down here at this corner, we're changing from fairly negative to fairly positive. So we're going to have this dot is going to be where our negative part stops, and we're going to have a dot up here for where our positive derivative is going to begin. Let's also see if there's any smooth turnarounds. I see one right here. And this one is kind of ambiguous. I'm not really going to count this one, although it gets pretty close to 0. So let's go through and get our signs for our derivative now. We're decreasing to start off with. Then we're increasing, decreasing, increasing, still increasing after that vertical tangent, then decreasing, and then increasing, so positive. Let's go through and see what we've got. We're starting out negative, and we've got to approach that asymptote. So the only way to do that, we're starting off with less of a slope and getting steeper, infinitely steep. So we need one of these downward branches going on. Here we're starting off infinitely steep. Then we have to go through this x-intercept. So we're starting positive, going through here, and approaching this other asymptote. Here we're starting off infinitely steep, but we have to end up infinitely steep as well. So this is a little tricky here. We're starting up here. We have to end up here. We never quite get to 0 for the slope. So we're going to have one of these turnaround kind of deals. It's kind of odd when you see those, but they do happen. Here we're still infinitely steep, but we're getting closer and closer to a slope of 0. So we need to kind of wind down into this direction. Here we have a constant negative slope, so horizontal line. And here is a constant positive slope, so horizontal line above the x-axis. Here's where we started. Just for your reference, you can pause it and study it more closely. And here is where we ended.